So we've just used superposition to solve for the strains. We took contributions from each of the normal stresses, and then we found that with the shear stresses and shear strains, right, we just used the stress and strain that related to each other. There was no Poisson effect. But adding all of those contributions together was a form of superposition. We solved it by pieces and then added the pieces together. So there are a couple of requirements to be able to use superposition. So the system, for one, has to be linear. And so mathematically, that means that we have to be able to get the solution to two variables. The addition would be the same as the answer with one variable added to the functional answer for the second variable. And the second requirement is that it's got to be scalable by a non-zero factor. So if we take a input argument, multiply by a non-zero factor, we would end up with the same answer if we took that factor and multiply it by the functional answer. So in what we're doing with materials, what this means is that we have to be in the linear range, right, where stress and strain directly relate to each other. So once we go past the yield point and we go into the nonlinear range of a material, this approach would no longer work. Right? The stress and strain would not be scalable by the Young's modulus E. Now, just as a quick note, although we're down here, right, in the small strain region, we end up with values of stress that are significant. So just keep that in mind. These values of stress are important. They're going to be stress values that we use in a design sense, continually coming up within the quarter. The other requirement would be that combined loadings must not affect each other. So I'm going to use an example here from a transverse deformation in a beam and relating it back to axial deformation. So the effect you're about to see needs to be negligible. So if we had a beam simply supported with a point load right in the middle, we would have a deformed shape that looks something like the picture below. Now, realize we talk about a neutral axis, and that axis has no strain on it, no stress. But if you notice here, the deflection due to the deformed shape would actually create the appearance of strain in the axial direction. So that would just mean the sort of geometric effect here would have to be insignificant. So stresses, and here bending stresses, couldn't create a net axial strain in our structure. So just recapping a little bit, when we go back to a uniaxial stress state, which again was probably one of the first things you were exposed to, and this would be with the specimen with a state of stress in this direction creating strain in this direction, although it also creates strain in the lateral direction. So here would be the normal stress and the strain in the direction of the stress. So if this was sigma xx, this would be epsilon xx. So we've got a linear range that we have to remain in. And as soon as this Young's modulus starts to yield, at some point we end up at a yield point where the material leaves the elastic range. So for this all to work, we need to stay in the elastic range. So here's a couple other pictures, a couple things to point out. So there are different stress values. Looking at that picture above, you would notice that the cross-sectional area, as the load applied, is going to decrease. Now what we'll end up using is also called engineering stress. And all we do is keep a constant in our calculation. Although it's not constant, we're going to remain using the initial unstressed cross-section as the stress calculation. So that ends up with the red line down here. If you were to take into account the fact that the cross-sectional area is decreasing, then you would end up with a slightly different stress-strain curve. This is what we use in engineering circles. We would just use the engineering stress. It's also comes up in strain, where strain is equal to the change in length divided by the original length. But if you did this calculation at each increment then you would end up with a different initial length. So there's also engineering strain and true strain. So in summary, we've connected the 6 components of stress to strain. We're restricted to linearly elastic, and it has to be isotropic in that the material properties are independent of orientation. All the materials we deal with will be isotropic in this class. So looking a little bit more at some Poisson's ratio values. So for different materials, you have different values for Poisson's ratio. So rubber is close to 0.5. Cork is all the way down on the other end of the spectrum, down to almost 0. So we will prove that these values need to be between 0 and 0.5, and actually not including them, not including the end value. So that's a range of values for Poisson's ratio that we'll have. So for the most part, we're going to end up with some materials right around in here. Steel is a common material that we'll use. So you'll see Poisson's ratios between 0.25 and 0.35 generally in this course. And so thinking about rubber, you think of a rubber band. If you go ahead and took a rubber band and pulled on it, you would see it. You would be able to see the Poisson effect as you did that. You would see the lateral contraction. If you took cork, right, for one, it's real hard to do that, but even if you could do it, you don't have a whole lot. If you tried to apply a axial compression, you would not have much expansion. So that's why cork is used in bottles, because when you put it in, it doesn't want to try and push its way out. So the last thing we'll do is derive a relationship between E, G, and Poisson's ratios. This is on your equation sheet. Again, this is for isotropic materials. So we're going to do this through a kinematic argument here. And this is extremely useful because this is hard to do in a testing lab. It's physically hard to hold a specimen and shear it. So instead of actually having to find the modulus of rigidity, we can use E and Poisson's ratio, which are calculated in a uniaxial test. So we'll go through that in just a minute, just to keep the conversation in that direction. Right? The uncoupling that occurs in the analysis of normal stress and shear stress, right, and the strain creation, right, those were completely uncoupled. Anything that was in the shear stress, shear strain, did not produce direct stress or direct strain. But however, the properties E and G, the material properties, do relate to each other. So I'm just going to quickly go through this. You're not responsible for this derivation, but I'll go through it with you. So to do that, we're going to take an element that is subjected to pure shear. Right? So there would be one shear stress. There's another shear stress. This is why when we say we know the shear stress on one side, we know it on all 4 sides, because it has to have the same value and it has to have relative orientation. Again, if not, if we summed a moment down here, this element would be spinning if we were to do equilibrium on it. So over here we've got a deformed configuration. And so we're going to take that element and we're going to rotate it, right, to the gamma over 2. And we end up with a deformed shape. And we're going to track this distance right here. So this distance, which is this value before in the undeformed shape, now has a strain in the diagonal. So a shear strain, shear stress, produces normal strain along the diagonal. So we're going to track this thing in 2 ways here. So let's just go and highlight that top portion of it. So we've got the sides L. We've got along its length, I'm going to call that length CB. And then we're going to have angles that have been created. So over here we've got an angle that originally was pi over 2 or 90 degrees. Added to it is going to be 2 epsilon xy, the shear strain. Down here we've got an angle that would be a little pi over 4 minus epsilon xy. Up here, same thing. And so we're going to use the law of cosines. And the law of cosines is given to you right here. And so side C is going to be LCB. So if we go ahead and write out the equation, we've got a and b squared minus 2ab squared times the cosine of the angle. And so that's going to give us equation 1. We have an expression for the length of CB in terms of the shear strain. Also, if we think of this in terms of direct strain, we would have a strain right along the diagonal. So I'm going to go back up here, and we've got a change in length along the diagonal. It was originally this length, and now it has a different length. So the length of that is going to be root 2 times L times the quantity 1 plus epsilon diagonal. So here's how we came up with that. Strain along the diagonal occurs if change in length of the diagonal over the length of the diagonal is a non-zero number. So the change in length would be the length of it, LCB, minus its original length. So this is after deformation, and this would be the length of it before deformation. So again, on the bottom we have that same quantity. So we're just going to do a little bit of math. We'll take over to the left-hand side the denominator, and then we're going to isolate LCB. So we'll take this term to the other side by adding it, LCB, and we'll factor that term out. So now inside the parentheses we've got 1 plus epsilon diagonal. We'll do just a little bit of math right there, simplify it. We get root 2L times 1 plus epsilon diagonal. So we've got two expressions for strain on for the length of the diagonal after the loads are applied, the shears are applied. So to finish this, we're just going to take those two equations and set them equal to each other, because we've got two equations that both contain LCB. And so we'll take it and square it here. Set it equal to each other. We end up with, on the left-hand side, an expression. Over on the right-hand side, right, there would be equation 2 over here. Here would be equation 1, the expression for LCB squared. Right, again, that equation 1 was from the law of cosines. So we'll cancel L squared out because it shows up in each term. So a little bit of simplification here, just some math to bring us home. So we would end up with an expression right over on the left-hand side. We just have a 1 minus the cosine left. And the other thing we've done is divided by 2 in all those terms. So there's where the 1 comes. We've got a cosine. On the other side, we just got 1 plus epsilon diagonal squared. So the 1's will cancel after we multiply out the left-hand side. FOIL method. We use a trig identity to get from a cosine to a sine. And we use the small strain necessity here. If it's extremely small strains, that term goes to 0. And the sine of something extremely small can be approximated by itself. And so we cancel out the 2, and we have the result that is going to help us here in just a minute, that the epsilon xy is equal to the strain on the diagonal. All right, again, this is a direct strain. This is a shear strain. So your first transformation, and this is the first of many starting in week 5 for us. So here's the original element with the shear stresses applied. We're going to now take this element and orient it at 45 degrees, and we will get very good at doing these transformations, but when we do that, when we transform this element, we end up with a normal stress. Now think of these as magnitudes right now. So those have values to them. So I'm going to use the value right here, and when I transform it, I'm going to end up with a tensile stress and a compressive stress. And so we'll take and then apply 3D Hooke's law to calculate strain on the diagonal. So I'm going to take the direct stress, which is sigma xy divided by E. I'm going to subtract Poisson's ratio times sigma xy over E. Those are in compression on the lateral faces, so that's going to end up giving me a positive term. And so I just simplify on the right-hand side, and I just set them equal to each other. There's an expression for epsilon diagonal. And so epsilon xy is going to be sigma xy divided by 2g, and epsilon on the diagonal would be given by this expression. So set those equal to each other. Sigma xy cancels, and we end up with our relationship between E, G, and Poisson's ratio.